Welcome to Mrs. Z's Chemistry. In this video, we will talk about isotopes. This is a continuation of 2.3. An isotope is a different atom or a different version of the same atom. Imagine you have two magnesium atoms. They both, of course, have 12 protons, but one of them will only have 12 neutrons, giving a mass number of 24, and the other one might have a different number of neutrons. Say 13 neutrons, giving it a mass number of 25. The positive 2 charge just means they both have lost 2 electrons, but that is irrelevant to the isotopes. Here's another element symbol. You have helium with 2 protons. It also has 2 neutrons, giving a mass number of 4, and it's lost its 2 electrons, so it has a charge of positive 2. In a text, if you were to look up this concept online or in a textbook, C14 means a mass number of 14 for the atom of carbon. This would mean, because carbon always has 6 protons, that C14 has 8 neutrons as well. Let's do a quick review. Mass number means protons plus neutrons. It must always be a whole number. Mass number is not written on the periodic table because the number of neutrons are not written on the periodic table. Each atom has multiple different versions, so the periodic table would have to show 2 to 10 different atoms for every single element, and that would be way more complicated than it already is. The mass that is on the periodic table is called the atomic mass or average atomic mass, and it is the weighted average of all of the isotopes. Since all isotopes weigh a little bit different because the different numbers of neutrons give it a different mass, then we have a weighted average to calculate that average atomic mass. In nature, each isotope has a certain natural abundance of how it exists. Let's look at a chart here. We're going to look at lithium. Lithium has 3 protons, so its atomic number for each isotope is 3. The number of protons for each isotope is 3. One lithium isotope has 3 neutrons, giving a mass number of 6. The other isotope of lithium has 4 neutrons, giving a mass number of 7. Here are the percentages for the natural abundance. Lithium-6, the one that has a mass number of 6 with 3 neutrons, it exists as 7.59% of all the lithium atoms in nature. 92.4% of all of the lithium atoms, basically the rest of the lithium atoms, are lithium-7, the lithium atoms with 4 neutrons. Most elements exist naturally as a mix of 2 or more isotopes. The average atomic mass, or atomic mass, is the weighted average of all of the isotopes and their natural abundances. So in order to calculate this, we need to multiply the percent abundance times the mass of the isotope, and then add that to the second isotope mass multiplied by its percent abundance. The equation looks like this. We have the mass of one isotope times its relative abundance, plus the mass of the second isotope times its relative abundance, and then you keep going if you have a third or a fourth isotope. The percent abundance must be written in decimal form. So if the percent abundance is 68.34%, you're going to multiply 0.6834 by the mass. And this is so that all of the percent abundances, since they should add up to 100%, in their decimal form they should add up to 1, because that's all or the whole of the element that we are discussing. The isotope with the greatest percent abundance is the isotope that is more common in nature. Therefore, make sure you are multiplying the correct mass with the correct abundance, or your weighted average will be incorrect. So here's a sample problem. The element boron is composed of 2 isotopes. About 19.9% of all boron atoms are B10 with a mass of 10.0129 AMU, and the remaining 80.1% are B11 with a mass of 11.0093 AMU. Calculate the average atomic mass of boron. The unit AMU is just the unit we're using to measure one atom. I'll give you a moment to pause and work this out. Here's how you would solve this problem. Here's the percent abundance of 19.9% in decimal form, and we're going to multiply it by this mass of the B10 element. Then you're going to add that to the percent abundance. This is the 80% 0.1% times its mass, 11.0093. When you add those up, we get 10.81 AMU, which if you look on the periodic table, that's exactly the average atomic mass for boron. Let's do another sample problem. A meteorite found in central Indiana contains traces of the noble gas neon picked up from the solar wind during the meteorite's trip through the solar system. Analysis of a sample of the gas showed that it consisted of 3 isotopes, with these percentages corresponding with these masses. What is the average mass of the neon in the solar wind? Pause and work this out. So here's how you would set up the problem. Each isotope, the mass multiplied by its relative abundance, and then we come out with 20.15 AMU for the average atomic mass of the neon found in the solar wind. The average mass of a neon atom in solar wind is 20.15. The average mass of terrestrial or neon on Earth is 20.18 AMU. This demonstrates that we may find slight differences in the natural abundances of isotopes depending on their origin. Here's another example problem. Pause to work this out. And here's your answer. Naturally occurring chlorine consists of chlorine 35 with a mass of this and chlorine 37 with a mass of this, with an average mass, which means the average atomic mass, of 35.453. What is the percent abundance of chlorine in terms of these two isotopes? So we can set up the problem. We're going to set up chlorine 35 over here. It has a mass of 34.96885. And we're going to multiply it by its percent abundance, which will represent as an X for right now. The chlorine 37 atom we'll put over here. It has a mass of 36.96590, and its percent abundance will be Y. And the average atomic mass is 35.453. So now we need to solve for X and Y. In order to solve for two variables, we need a second equation. Well, because the percentages of all of the isotopes is going to equal 100%, we can say that X plus Y is equal to 1 because we're multiplying the percent abundances in their decimal form. So now we can solve with substitution and find what X and Y are equal to. Naturally occurring copper consists of copper 63 with this mass, copper 65 with this mass, and an average atomic mass of 63.546. What is the percent composition of copper in terms of these two isotopes? Pause and work this out. Here is the worked out problem. We have our first equation set up right here. Our second equation is X plus Y is equal to 1. We can convert that into X is equal to 1 minus Y and then solve with substitution with this step and then distribute. And now we combine like terms and we get that Y is equal to 0.3085, then X is equal to 0.6915. Turn those into percentages, and here we have our answers.